All right, good morning, gentlemen. How many people here? Han, he is here, Atwisal, Papaya, Leng Sun, and Chan Makara, 5 people. Okay. One, two, three, four. Guys, I hope you can hear me. Let's start. Now we are in 4.3. Today we'll talk about homogeneous linear equations with constant coefficients. Okay. About midterm, actually your midterm is scheduled next week, but you will have midterm maybe after next week. But first we have to finish chapter 4. Then you will have midterm. And I will let you know about the dates. Davids. Okay. Papaya, can you hear me?
Yes, sir.
Okay, very good. So actually we were studying chapter 4, higher order differential equations. And in 4.1, you were introduced with some fundamental concepts, definitions, and theorems, right? About linear equations, initial value and boundary value problems, homogeneous equations. Now we know what we mean by homogeneous equations, and also non-homogeneous equations, and fundamental set of solutions. And after this, we studied reduction of order, and what we mean by reduction of order, the order of the differential equation. By making some substitution, we can reduce this step by step. Maybe if the order is 3, by making one substitution, we can reduce this to 2. If it is 2 to 1. Okay, and to do this one, actually, if suppose that if you're given one particular solution, right, and using this one, we actually developed a technique to find the second one, the second solution. And after that, using these solutions, what is it? We wrote the general solution of the differential equation of the second order. Now today we'll be talking about homogeneous linear equations with constant coefficients, okay? But it's a special case, constant coefficients, when the coefficients are not constant, and we will see some examples later, okay? So, after this, we will study this 4.4, undetermined coefficients. And this 4.5, 4.4, they are same topics, but different approach. Okay, that's why I'm going to skip this 4.5. And if you're interested, you can study yourself. Just learning one of these methods will be enough for you. And 4.6, variation of parameters. We will study this, very important one. 4.7, Cauchy-Euler equation. And 4.8, again, we will skip this Green's function. We will not use this much. It's also important, but we are not going to say this in this course because we don't have much time. And 4.9, solving systems of linear equations, differential equation by elimination, and non-linear differential equations. Okay, so here, introduction. Actually, before we start this, if you remember, let's consider this example. This ay prime plus by is equal to 0. Here, let me just correct this mistake. Okay. Vishal, we can see the slide, right?
Yes, sir. Yes.
Okay. All right. Now we solved this kind of equations in the previous chapters. Ay prime plus by is equal to 0, right? Now to solve this one, what did we do there? The first, if you just take this this ay prime plus by is equal to 0, right? I can write this as y. We can write it as y prime is equal to minus b over ay, right? And now if I just denote this negative b over a minus b over a as a, then here we will have y prime will be equal to m times y, right? And how do you solve this? If you remember, this is something like this, right? dy over y is equal to m dx, right? And then if you just integrate both sides, what we get here, here we get natural logarithm of y and is equal to, here we have mx. Let me just ignore the c for now, or we can just write c, doesn't matter. Okay, now from here what we get here, that this y is equal to something like this, right? Y sub 0 times e to the power mx. Okay, and from this equation, here we have y prime is equal to m times y, right? Do we know any function when we just differentiate this? Okay, it just gives us constant multiple of it is the original function, right? And the only function in math is exponential function. When you just differentiate this, right, is equal to itself. Again, actually, the result, right, differentiated function will contain the original function. Okay. Usually, if you differentiate a function, a new function contains the original function. What kind of functions are this? Maybe if you differentiate twice or 3 times or 4 times, that one is exponential function or sine function or cosine function. Not any function at all, right? These 3 functions are really important. Now, from now on, you will see that when we just solve differential equations, and most of the time, maybe all of the time, you will see that in the solution, actually, our function contains exponential function or and sine of x or sine function and the cosine of function. Okay, so from this motivation, actually we will use this idea to solve our nth order linear differential equation with constant coefficients. Okay, because here we'll just assume that if you're given this differential equation, okay, and I assume that this solution is, let's say, y is equal to e to the power mx. And after that, I substitute this. Okay. And after that, when we just do some algebraic manipulation, you will see that we will get nth degree polynomial equation. Okay. And these two things are very closely related to each other, this differential equation and nth order polynomial equation. Okay. So now in this part of the chapter, in this section, we will learn how to solve this kind of equations. Homogeneous, because on the right hand side we have 0, and all these coefficients here, they are constant, not functions of x. Okay, that's why it's a special case. Okay, now we will start with the second order differential equation. Let's say we are given a special case. Let's consider this differential equation. Our differential equation is a y double prime plus b y prime plus c y is equal to 0. Okay, how do you solve this equation? Now for this, if I just assume that its solution is something like this, y equals e to the power mx, right? Now, since I'm assuming that this is a solution, when I substitute this, it must satisfy this equation, right? When I just substitute here, differentiate this twice and differentiate this once, and here the function itself, after that just evaluate this expression, it must produce 0. So here, what is y double prime? Y double prime is equal to m squared times e to the power mx, right? How about y prime is equal to m times e to the power mx? And y is equal to e to the power mx. Now if I substitute here, we get a times y double prime is m squared times e to the power mx plus b times y prime. That is m e to the power mx, and here we have c y e to the power mx, which is equal to 0. And we are hoping this is equal to 0. Now, as you see here, e to the power mx, right, is a common factor. If you just extract this or take this out, here we have a m squared plus b m plus c is equal to 0. This is second order, right? If it's the third order, if you just follow these steps, here we will get third degree polynomial equation. If it is fourth order, here we get fourth order polynomial equation. And how about if we have the order is n, let's say function is n times differentiated here, then here we get nth degree polynomial equation. Now, how do I solve this equation? Here it's not m squared, right, is equal to, we are taking this thing out, e to the power mx, right? Now, something times something, right, is equal to 0. We know this in math, in real number system, if a times b is equal to 0, right? If and only if a is equal to 0 or b is equal to 0. So here in this case, here we have e to the power mx should be equal to 0, or a m squared plus bm plus c should be equal to 0. And we know that this exponential function e to the power of something is never equal to 0. So here we have no solution, right? We have no solution. So here we have solution. We have, because this quadratic equation always it has solution, right? Either it's real or complex, but always it has solution. Okay. So actually, to solve this problem, we need to solve this equation. And after that, from here, if I can find m, right, m equals something, m1 equals something, because the quadratic equation has two solutions. And if I just substitute here, we will get the solutions of this differential equation. Okay, and we just, it's a special equation. We call this auxiliary equation. Okay, we call this auxiliary equation. So to solve this one, we know how to do it, right? First, to solve this quadratic equation, we need to find discriminant. That's equal to b squared minus 4ac. And after that, here we have m1 is equal to minus b plus square root of delta over 2a. And m sub 2 is equal to minus b minus square root of delta over 2a. Okay. So actually here we have three different cases, right? Depending on the value of this discriminant. So we will consider these three different cases separately. The first case is, what is it? Delta is greater than 0. At the time, here we will have two real roots and m1 is not equal to m2. We will have two distinct real roots or real distinct roots. Okay, and what is the second case? Second case is delta is equal to 0. If delta is equal to 0, we will get two roots, but they are equal to each other. So we call them repeated roots, right? And third case is, what is it? Delta is less than 0. And also here we get two solutions, but they are not real, they are complex, right? So we get two equations, and we will consider one by one. And the first case, assume that this delta is greater than 0. Distinct real roots, right? In our case here, again, we are talking about this equation plus by plus c, by prime plus cy is equal to 0. So in this case, our discriminant is greater than 0. That means that we get two solutions, m1 and m2, right? They are not equal to each other, and both are real numbers. Right? So at that time, if you just substitute our solution is in this form, right? We get the first solution, sub 1 is equal to e to the power m sub 1 x, and we get the second particle solution here, that's equal to e to the power m sub 2 x, right? And these two things, since M1 and M2, they are not equal to each other, these two solutions are, what is it? Linearly independent. Because if you multiply this by constant number, it never produces this number. These are exponential functions, right? So these are linearly independent. And it's a second order. It has only two fundamental, what is it, solutions. Then all possible linear combinations of these functions gives us or produces, what is it, the general solution of this equation. Then I can write here, then the solution of this differential equation is, what is it, y of x is equal to c1 times e to the power m1x plus c2 times e to the power m2x. It's the first case, and that is the solution of this differential equation. Okay, we are considering here the second order. Maybe the third order at the time. How many functions will we have here? We have f1, f2, f3. This fourth order at the time 4. f1, f2, f3, f4. Papaya, are you there?
So yes, sir.
Is everything clear?
Yes, sir. So are you at San Francisco, sir?
Sorry?
Where are you, sir?
Where am I?
Yes, where are you?
What do you mean? I am in Phnom Penh at university.
But your background is not Phnom Penh.
Okay, I see. Now I got your question. Because I don't see myself here. Did I? Do I see? Where is it? Okay. Oh, this is a bridge. I just found out here. I was checking some properties of Zoom, and there was 4 possible backgrounds. I just used this one. Okay, next time I will find better backgrounds if it is attracting you. If looks nice to you, guys. If you, as you see, that's very, I don't know, but not very complicated, quite easy. Okay, we are just supposing that actually. You may wonder, the question comes, okay, Mr. Custom, how do you know that we have to expect or suppose that the solution is in the form e to the power mx? Okay, this didn't happen in a few days or in a few months, all right? When people started dealing with differential equations, they were doing research and developing the techniques, and they tried a lot of methods, and after that, eventually, actually, it is the only case that the solution of this differential equation is this form. It doesn't have any other solution. If it's any solution, it must be written as a linear combination of these two functions. Okay, so second case, now we'll talk about, see examples of it later. Repeated real roots. Okay, so repeated real roots. Here we are talking about, again, this differential equation plus by prime plus cy is equal to 0. So now here delta is equal to 0. Okay, so at the time the first solution will be the first one here, m1 is equal to m2. As simple, it's just equal to m, right? Because two things are equal because only one solution, but it is repeated, right? Because we say that it is algebraic multiplicity of this root is 2, because we can write it as, what is it? M minus m1 squared is equal to 0. So it gives us the first particular solution, that y sub 1 is equal to e to the power mx, or m1 or m2, both is equal to m, just denoting with m. Okay, now we need to find the second solution. How do you find the second solution? In the previous section, if you are given one particular solution, and we learn how to find this second solution, right? And now I'm just looking for the second one. Y sub 2 must be something like u of x times e to the power mx, right? Now if you just substitute this and blah blah blah, we will get u to y2, right? Now what is y2? If you remember, the formula was y2 is equal to y1 times integral and here we have e to the power minus integral p dx, and here we have y1 squared dx, right? And what is this integral? From here we can evaluate this e to the power minus p, right? And what is p here? Here p is minus b over a, right? Minus b over a. Because here, if we just write this in standard form, we have here y, it's double prime here, double prime plus b over a, y prime plus c over a, y is equal to 0, right? And what is it? It is linear second order differential equation, right? And what is this thing? Now from this equation, when you solve this, if you remember, our delta is equal to 0, and here m is equal to minus b over 2a, right? Minus b over 2a. Okay. Now from here, just we can find that then what is b over a or minus b over a? Because here we have minus, right? Minus p means minus p is equal to minus p b over a, right? Now from here, what is minus b over a is equal to 2m. So from here, in our case, here we have p dx that's equal to e to the power, what is minus p is equal to 2m dx. That's equal to e to the power, what we have here, 2mx, right? Now if I substitute here, y sub 2 will be equal to, what is y1? E to the power mx times integral, and this thing is equal to e to the power 2mx over what we have here, y1 squared. What is y1? y1 is e to the power mx. So here we have e to the power 2mx because of the square, and dx. That's equal to 1. And if you integrate this, is equal to x. So that's equal to x times e to the power mx. Okay, and that is really important. Now we got the second particle solution. And you see here, e to the power mx and x times e to the power mx. These are linearly independent functions because they are not constant multiple of each other. Now I can write, if the roots are equal, then the solution of the given differential equation is C1 times e to the power mx, all possible linear combination of these two functions, right? C2 times x e to the power mx. Okay. And now you will see that if the order was 3, and if we have repeated root, it will be here x times e to the power mx. Next one will be x squared times e to the power mx. Anyway, we will just see the general case a bit later. Okay. All right, so far so good. I will continue. How many minutes we have? 11. Let's see one more case maybe, or guys, how many minutes passed? Langston? Langston. Okay. Maybe you are busy. Guys, let's have some break, okay? Now it is 11:03. At 11:10, we will continue from here. All right? Let's have some break. 7 minutes break.